Let's take a look at the next section in Chapter 2, Section 2.4 on matrix inverses. Okay. So this is a very important concept with regard to performing matrix algebra. So given a square matrix or a matrix of size n by n, same number of rows and columns, the inverse of A, and we call that, we indicate that with a to the minus 1, kind of reminding us of a reciprocal, satisfies A times its inverse is equal to the identity matrix. If A is n by n, A inverse will also be n by n, and then the product will be n by n as well. And then it also satisfies A inverse A is equal to I. So we see that A and its inverse commute with respect to matrix multiplication. And remember, that's a special case. That's not true for two matrices in general, even if they are two square matrices. So it is true too that only square matrices have inverses, but not all square matrices are invertible. So A inverse doesn't exist for all square matrices. So let's look at an example, a simple example to illustrate this. So for example, let's take the case that A is equal to 1, 1, 0, 0, and then I'm going to let B be a completely arbitrary 2 by 2 matrix with all four elements unknown and indicated by A, B, C, D. Okay, so if we look at the AB product, since A is 2 by 2 and B is 2 by 2, so the first row of A times the first column of B, I mean this element is A plus B, this element of the product, and then the first row times the second column would give us B plus D. And then if we look at the bottom row, which is all zeros, times the first column and the second column, we get this result. Now, again, B is completely general, so we see from this result that it's impossible for this to be equal to the identity matrix, which has a 1 on the diagonal. There's no way that 0 is equal to 1. So AB cannot equal I. So there is no B matrix that is the inverse of A. So the inverse of A does not exist in this case. Okay, or we would say that A is not invertible. Okay, so we've looked at a simple example of a matrix that does not have an inverse. How do you find an inverse? Well, let me erase the board. We're going to take a very simple case, and on finding the inverse of a 2 by 2 matrix. Okay. And so again, I'm going to keep this completely general. So I'm going to leave all four elements of the 2 by 2 matrix, write them as variables A, B, C, and D. Okay. And then and to write down the formula for the inverse, we also have to define the determinant of a matrix. Determinant. It's indicated determinant of A. It's equal to the AD product, so the product of the terms along the main diagonal minus the product of terms along the off diagonal, so AD minus BC. Now this definition is only true for a 2 by 2 matrix. The determinant exists for larger matrices, but the formula is more complex than this. But the formula for a 2x2 matrix is fairly simple. And then the adjoint matrix. Now, some texts refer to this as the adjoint, but the adjoint typically means something else in modern linear algebra. So it's more properly referred to as the adjoint, but you may have heard it referred to as the adjoint matrix previously. And then for the adjoint, now the determinant is a single number, okay? You know, here's the product of these two elements minus the product of those two will give us a number. The adjoint is another matrix, okay? And the adjoint is defined as we swap for a 2x2 matrix, we swap the elements along the main diagonal, and then we negate the elements along the off diagonal. Okay. Now, just like for the determinant, there's a definition of the adjoint that exists for larger matrices, larger square matrices, and we'll see that later in a later chapter, actually. But these are the definitions for a 2x2 matrix. And then the inverse of a 2x2 matrix then is 1 over the determinant. So again, this would just be a number times the adjoint matrix. So the result is a matrix. Now, should point out here that the inverse exists. I'll write this down actually. The inverse exists only if the determinant of the matrix is not equal to 0. If it is equal to 0, we've got 1 over 0, and so this, which doesn't exist, and so the inverse doesn't exist. Notice that the adjoint is always going to exist, but 1 over the determinant does not exist if the determinant is equal to 0. So again, you could actually go back and check on that previous example where I said that the inverse did not exist. You could show quite easily that the determinant of that matrix was equal to 0. So again, this will be true in general. For larger matrices, if the determinant is 0, the inverse of the matrix does not exist. Okay. Okay, so let's look at a simple example of an application of this. So we'll use this example, 5, 7, minus 3, 4. So the determinant of A is 5 times 4, the product of the elements along the main diagonal, minus the product of the elements along the off diagonal. So this would be 20 minus a negative 21, or 41. And then the adjoint of A is equal to, we swap the elements along the main diagonal and then take the negative of the elements along the off diagonal for a 2x2 matrix. This is the definition of the adjoint. Okay, so A inverse would be 1 over 41 times 4, 3, minus 7, 5. Okay, or let me write that a little differently. 4 over 41, 3 over 41, minus 7 over 41, and then 5 over 41. Let's take a look at the A inverse product. Now, if we've truly found the inverse, this should be equal to the identity matrix. So I'll take the first row of A times the first column of A inverse to get the upper left element. So that's 5 times 4 in the numerator, 20 over 41, minus 3 times a negative, so that's actually going to be plus 21 over 41. And that's going to give us 41 over 41, or equal to 1, so that looks good. For the element in the upper right, we take the first row of A times the second column. This is the 1, 2 position. So the first row of A, first row of the first matrix, times the second column of the second matrix. We're going to have 15 over 41. And then we'll have minus 3 times 5 over 41, so minus 15 over 41. Again, that's equal to 0, so again, that's good. That's what it should be if this is going to be equal to the identity matrix. Now the bottom row of A times the first column to give us the position in the 2, 1 element, we'll get 20 over, sorry, that's 28, 7 times 4. 28 over 41 minus, I'm sorry, minus 4 times 7, so plus 4 times a negative 7, so that's minus 28 over 41. Again, that's going to be equal to 0. And then for the last term here, we have this row 7, 4 times this second column, so that's going to be 21 over 41 plus 4 times 5 is 20 over 41, and we see that is equal to 1, 0, 0, 1. Okay, so verifying that this is indeed the inverse of the matrix above. We could also verify that A inverse times A also is equal to the identity matrix. I will point out here, without proof, that matrix inverses are unique. Okay. What that means, if you find the inverse of a matrix by any method, by showing that A times some other matrix is equal to the identity matrix, then that matrix has to be the inverse. There is one and only one inverse of a matrix. Okay. So I'm going to break this lecture up into several smaller short videos. So you can take a little break between videos. So I'm going to stop this video and come back with talk about the next section in just a minute.